Come on and cry me a river, cry me a river. I cried a river over you.
Good morning and welcome again. How are you doing? I hope you're doing fine. I'm okay as well. I hope. So, welcome to this Wednesday, the 8th of July 2026. I have a couple of fun facts in the form of an article, of course, as always, and a thread as well. I don't know how much are we gonna be able to cover, but let's see how it goes. First in line, we have this one. Very short and cool. Uh-oh. That's not the one I wanted, sorry. We're starting with difficulties, technical difficulties, again and again, but we're not gonna surrender. Not, never. Here we go. Octopuses fall for the rubber arm illusion, just like us. Experiment shows octopuses feel body ownership, a trait previously seen only in mammals. Oh, I thought just in humans. Let's see. Supposedly he's getting scared by something? I don't know. Let's read to better understand. The human brain can bring rubber to life with one simple trick. Cover a person's hand and place a rubber hand next to it. Then stroke their hand and its facsimile, and suddenly the person will begin to feel the touch in the fake appendage. The rubber hand illusion helps demonstrate how our senses work together to create the feeling of ownership over our bodies, a fundamental part of self-awareness. And now, a new study in current biology demonstrates that octopuses fall for the rubber arm trick, the first documentation of this phenomena outside of mammals. Researchers at the University of Ryukyus, placed a plain-body octopus, Octopus aspilosomatis, into a tank filled with polymer beads. Whenever the cephalopods sat on the beads, the team covered one of the limbs with a fake arm affixed to an opaque sheet, and then gently stroked both arms at the same time. When the researchers pinched the fake arm with tweezers, the octopus reacted defensively by changing its body color. Oh, I didn't see that. Retracting its arm. findings suggest octopuses perceive a similar level of body ownership as humans and other mammals, highlighting the complexity of the squishy eight-armed creatures. Cognition. The spineless animals have a complex nervous system that evolved independently from vertebrates, and also seem to have multisensory representations of their own boneless bodies. Cool, let's see again the video. Where's that? Is this one? Yes. Okay, let's see the video again. Please. Not working. I'm not gonna insist because it might crash my computer. Here we go. So they need to be trained before the scary part, I guess. The changing color, where's the changing color? Not a great image, quality image. Okay, let's go to the next one. Logical reasoning does not involve language processing parts of the brain. A functional brain scan of a neurotypical participant in the study shows a distinct separation between logic, the green color, and language, red and yellow activations. Okay. Cool. Separating Logic and Language by Jennifer Michalowski. This is by McGovern Institute. Some people find it useful to talk through their problems, but language isn't necessary for logical reasoning. Cognitive neuroscientists at MIT's McGovern Institute say, in research published today in the journal PNAS, researchers led by McGovern Institute investigator Evelyn Fedorenko have shown that people can perform well on tasks that require logical reasoning even if their language abilities are severely impaired. What's more, brain imaging shows that language processing parts of the brain are not called on for logical reasoning. Fedorenko is also an associate professor of brain and cognitive sciences at MIT. Philosophers, linguistics, and cognitive scientists have debated the relationship between language and thought for thousands of years? Thousands of years? Okay, philosophers, yes. The other one, no. There are good reasons to suspect a close relationship between logic and language, acknowledged Hope Keane, a postdoctoral researcher and former ICON graduate fellow in Fedorenko's lab. Abstract thinking has properties that look a lot like language, she says, pointing to structural similarities. You can decompose a thought into subcomponents, like little atoms of logical propositions, and you can combine them in a hierarchical manner to make more complex structured rules, very akin to language. But she and Fedorenko suspected that while we largely depend on language to communicate about logical reasoning, from presenting a problem to explain how we have arrived at conclusions, the brain might use a separate system for the reasoning itself. There are aspects of thinking that seem to go beyond some of the limitations of language, Keane explains. Logical reasoning demands precision that language often lacks. I agree. And language is linear, progressing one word at a time. Whereas evaluating available information to reach logical conclusions can require thinking in less linear ways. Yes, like large language models, right? You interact with it through language, but then the AI makes his own internal calculations based on numbers, of course, matrices, and so on. I think, at least, not an expert in nothing of this. A simple psychologist. Logical reasoning. These observations left King curious about how the brain handles logical reasoning. It's a particularly difficult question to answer scientifically, because it's hard to take language out of the equation when working with human study participants, but Fedorenko's team did just that by collaborating with Rosemary Varley, a neuroscientist at University College London who studies acquired language disorders, and her team. Together, the scientists worked with two patients who had experienced stroke that damaged language processing parts of their brains, leaving them with severe impairments in both understanding and producing language. They designed language-free logic games in which participants were asked to infer relationships between sets of numbers. Given two lists, they had to figure out the hidden rule that turned one list into the other, such as reversing the digits or removing numbers above a certain value. Once they thought they discovered the rule, they had to apply it to new examples. In a second game, participants were presented a set of geometric patterns and asked to identify another pattern to complete the matrix. As participants solved increasingly difficult puzzles, it became clear that people don't need language for this kind of reasoning. Patients with language impairments solved the problems as well as a control group, and were even able to communicate the rules they inferred using gestures or with a sketch. It literally appends a theory that says that symbolic rule induction is not possible without linguistic capacities, says King. Anatomical scan of two participants with several aphasia top row, and a projection of the probabilistic atlas for the language network into the MRI. I don't know what the atlas is, so let's continue. Alongside this part of the study, Keane and colleagues also used functional brain imaging to study what happens in the brains of healthy adults when they are engaged in logical reasoning. Participants in this part of the study visited MIT for a series of MRI scans, which capture images of their brain activity during an array of tasks. In addition to completing different kinds of logic games inside the scanner, participants were asked to engage in tasks designed to map the language processing parts of the brain. Another set of tasks was used to map each person's multiple demand network, a distributed brain system that supports complex problem solving. These neurotypical participants completed logic games similar to those used with the language-impaired patients. They were also presented with problems that required syllogistic reasoning using if-then statements such as, if the ball is red, then it is big. The ball is red. Is the ball big? The team varied the difficulty of the logic puzzles so they could see which brain areas became more active when the need for logical reasoning intensified. Likewise, they looked for changes in the brain activity when participants had to infer a hidden rule versus simply applying a rule they would be given. Oh, okay. Here, too, a separation between language and logic was clear. The MRI scans showed the brain's language system is not engaged for either inductive reasoning, when participants identified hidden rules, or deductive reasoning, when they assessed the validity of syllogistic conclusions. Surprisingly, the multiple demand network, which many scientists had suspected was important for logical reasoning, was engaged during inductive reasoning, but didn't seem to get involved in deductive reasoning, a finding King is building on in her ongoing work. For Fedorenko and King, the findings are strong support for a separation of logic and language in the brain. They add to previous findings from Fedorenko's lab showing that other types of thinking, such as object categorization and social reasoning, also do not rely on language. Acquired language impairments and AI. Acquired? The researchers say these findings have important implications for how we think about acquired language impairments or aphasia. Specialists who work with people with aphasia have long recognized that loss of language does not mean loss of intelligence. People with aphasia can continue to enjoy playing chess, solving Sudoku puzzles, or being in charge of the family's finances. But it is common for others to confuse their communicative difficulties with thinking difficulties. This research adds to a growing body of work establishing that even severely aphasic individuals can preserve their ability for abstract logical thoughts, a defining feature of our species, Fedorenko says. Okay, I think that's enough. Almost done. Anyway, what else? I think we're gonna do this one by Jasmine Khosrowshahi. Wow, what a name. Very difficult. And I don't know from what culture or language might come this family name. I don't know. If anybody knows, please let me know in the comments. Let's start. Waiting for the music. Okay. Stanford professor Judy Fang went on stage at MIT and broke down why humans are so good at making the invisible visible. There's a video down here, a 1 hour video. I'm gonna leave the link for the people who wanna. Oh, and we have the handle of the person. Okay. Making the invisible visible. And why AI hasn't actually learned to see the way we do. It completely changed how you think about human intelligence versus artificial intelligence. Number 1. Nature never gave us straight lines or sharp corners. The number line, the coordinate plane, even basic geometry are all human inventions. We created tools that do not exist in nature simply because we needed a way to think more clearly. Number 2, the coordinate system. The coordinate system Descartes invented solved a problem that had stumped mathematicians for centuries. Doubling the volume of a cube. Once invented, this tool became so indispensable that virtually every math curriculum on Earth still depends on it. Doubling the volume of a cube. Okay, I didn't know that was his great contribution. Very important, I suppose. Yes, very important, of course. Number 3. Humans have been doing this for at least 30,000 to 80,000 years. The story of human progress is inseparable from the story of making up our environment. From cave walls to Galileo's telescope to Feynman diagrams of particles, we will never see with our own eyes. Every major scientific breakthrough relied on a visual tool that made something invisible visible. Darwin needed side-by-side illustration of finches to see variation that was otherwise too subtle to notice. Cajal or Cajal needed detailed drawings of neurons under a microscope to map how the nervous system was wired. Number 5. Fans Research Group studies something. Fans Research Group studies something deceptively simple: how people decide what to put into a drawing and what to leave out. When two people played a drawing game, sketchers used far more detail when the target object had close competitors than when it stood alone, all the way down to using fewer strokes and less time when more detail was not necessary. Number 6. People are not just copying what they see, they are making constant judgment calls about what level of detail actually serves the goal of communication, and they do this naturally without ever being taught the theory behind it. Number 7. There is a real difference between drawing something so someone can identify it and drawing something so someone can understand how it works. In one study, participants drew explanatory diagrams that emphasized moving, causal parts of a machine, while the depictive drawings emphasized background and overall appearance, even though both were drawing the exact same object. Number 8. Explanatory drawings were genuinely better at helping someone figure out how to operate a machine, but worse at helping someone identify which machine it actually was. You cannot optimize a single drawing for both goals at once. Communications always involves trade-offs. AI vision models trained on photographs generalized surprisingly well too simple. Sparse sketches suggesting that resemblance-based recognition is not just a story we tell ourselves. It is something modern neural. I can't read this tweet, I'm sorry. It is something modern neural networks can replicate with real accuracy. Number 10. But there remains a large, measurable gap between how confidently AI models recognize sketches and how confidently humans do, even when both groups answer the same questions about the same images. Humans are simply far more reliable and far more consistent in their judgments. Number 11. When researchers compared human-made sketches to AI-generated sketches under tight stroke budgets, both were similarly recognizable at higher budgets, but diverged sharply as the budget shrank. Humans and AI systems simplify drawings in fundamentally different ways once resources get scarce. Number 12. Reading a graph is not one single skill, it involves perception, knowing where to look, mapping that visual information onto the actual question being asked, and then translating that mapping into an answer. Each of these steps can independently break down, and people fail for very different underlying reasons, even when they land on the same wrong answer. Number 13. When tested directly against humans on graph reading tasks, leading multimodal AI models, including GPT-4V, showed a meaningful performance gap. Even when a model's overall accuracy approached human levels, its pattern of mistakes looked nothing like how humans actually get things wrong. Number 14. People choose entirely different types of charts depending on what specific question they are trying to answer, not out of a generic preference for bar charts or scatter plots. Their chart choices closely tracked which visualization would genuinely help someone answer that specific question correctly. How many? Oh, we have just 2 left. Number 15. 2 of the most widely used graph literacy tests. No, we need to see the video to understand this sophisticated research, I guess. We have a gist, a quick overview of the subject. I hope you'll find it, or you could get something out of that. We have time for this one. I guess it's too long? No, it's not so long. MIT News on campus and around the world presents. The brain's language network is more extensive than previously thought. A new study reveals that parts of the brain located far from the canonical language processing centers are also involved in language comprehension. By Annette Rafton, MIT News, July 1st, 2026. For decades, neuroscientists have known that specific regions in the brain's left hemisphere are responsible for processing language. However, a new study by MIT researchers shows that language processing also occurs in many other parts of the brain. Using functional magnetic resonance imaging (fMRI) data from more than 700 people, the researchers identified 17 additional regions of the brain that appear to play a role in language. These regions are scattered across the brain, including parts of the cerebellum, hippocampus, and cerebral cortex, and they make up about 5% of the total volume of the adult brain, about the size of a large strawberry. Even though there are all these distant components, it's pretty restricted in terms of volume. You don't need that much of the brain to do language, says Evelina Fedorenko. Oh, we have Fedorenko again! An MIT Associate Professor of Brain and Cognitive Sciences, a member of MIT's McGovern Institute for Brain Research, and the senior author of the study. Exactly how these regions contribute to language processing is still to be discovered. Although the researchers have made some progress toward determining the functions of the cerebellar regions that they identified. MIT postdoc Agatha Wolna is the lead author of the paper, which appears in the Journal of Neuroscience. Other authors include Aaron Wright, A.K. Lisa Young, post-baccalaureate research scholar at MIT, oh my god! Colton Casto, a graduate student at Harvard University, Samuel Hutchinson, a graduate student at MIT, and Benjamin Lipkin, PhD. Tracking language or language. The brain's language processing centers include Broca's area, first discovered in the 1800s, plus additional regions in the left frontal and temporal lobes of the brain, scientists have found that some of the corresponding areas of the right hemisphere also contribute to processing language, especially the social emotional components of language. Of course, the right side is the more emotional side, though that makes sense, and a little bit of symmetry as well makes sense. There have also been hints that other parts of the brain might be involved in language processing. Early in her career, Fedorenko's language studies often showed active brain regions outside of the canonical language centers, but she says she was discouraged from including them in her papers. Why? When we initially started looking at language, in the first couple of papers, I tried to be comprehensive and include anything that seemed consistent across participants. And there was a huge amount of resistance, she says. People would say things like, well, we know those are not language areas, so please focus on the language areas. In the new study, she and Walna wanted to revisit those brain scans and see if they could systematically identify language regions outside of the standard language processing areas. To do that, they analyzed data from 772 people who had been scanned in Fedorenko's lab since 2013. Each of these participants underwent a task known as a language localizer, which is used to determine the location of language processing areas for each subject. During the test, participants read or listen to sentences as well as sequences of non-words. For each person, the researchers measure the difference in strength of response when reading real sentences or nonsense sequences. The brain areas that work harder during the sentence condition are considered to be doing something relevant to language, specifically if they respond while both reading and listening to sentences. It's a very simple paradigm that lets us identify this core language system in individual brains, Walna says. When searching for language areas, the researchers usually use a relatively strict statistical threshold. In this study, they relaxed the threshold and also used some targeted searches in subcortical areas in hopes of finding all areas that may contribute to language processing. We always see this frontal temporal network, but there's quite a lot of evidence that there are other regions that are also critical for language processing, Walna says. By using a laxer threshold and zooming in on areas with weak MRI signals, we try to maximize the chances of finding small and weakly responsive regions outside of this left frontal temporal system. A widespread network. For about 490 of the participants, the researchers also had data on how their brain responded during a spatial working memory task. Spatial. I don't know how to pronounce it, sorry. Remembering the locations of flashing squares on a grid. This task engaged a brain network called the multiple demand system, which does not overlap with the core language areas. Oh, we learned that in the other article, right? The logical part and the language part separation. This task allowed the researchers to ask whether any of the newly identified language-sensitive regions specifically respond to language and not more general cognitive processes. Okay, of the 17 new language sites that were revealed by this study, 5 are located in the cerebellum, which is mainly involved in coordinating the body's movement. In a study published earlier this year, researchers led by Casto found that 3 of those cerebellar regions also became engaged during some non-linguistic cognitive task, which was also seen in the new study. Those areas that respond to both language and some other tasks could be really interesting and important because they may be doing something like integrating information from different cortical systems, Fedorenko says. They also found language selective regions in the medial frontal cortex, the bottom surface of the left temporal lobe, the hippocampus, and the amygdala. The researchers now plan to further study how these brain regions might contribute to language processing. We can now test some ideas from past work and also more rigorously characterize these regions across different kinds of language manipulations and different kinds of non-linguistic tasks to try to understand what it is that they're doing, Fedorenko says. The research was funded by the Simon Center for the Social Brain at MIT, the McGovern Institute, MIT's Department of Brain and Cognitive Science, and the MIT Siegel Family Quest for Intelligence. Okay, good to know who's involved in this brain initiative. Okay, I think that's all for today. I thank you very much. I apologize for my horrible English and abilities to read some of the articles. Some parts, at least, sometimes are harder, so I'm sorry. I'm training myself, so you are just watching me training myself. Thank you very much. See you the next one. Goodbye.
Come on and cry me a river, cry me a river. I cried a river